Hi, good sir. Welcome to the class.
Hello.
You send me like 10 photos. Are they just work you're doing at the moment, or do all of them have questions that you don't understand?
It's actually both.
Okay, good. I've just pasted them so we can run through them.
All right. I think I sent them to.
Yeah, I've got them. I've got them. So I'll have a look at them. Welcome to the class, Benice. Make it very difficult for me. Rename. Okay, just get your mic up and running, Benice. I think you need to plug in something or allow, I don't know what you're working on a Mac or a PC or a tablet, what?
Shaal?
Yes,
Sorry.
hi.
Dis Limarie. Lisa's aan hier nie. Kan jy ook goed so, kan jy ons mooi hoor?
Ek hoor julle.
Okay.
My internet is dalk 'n klein bietjie onstabiel vir een of ander rede vanoggend. So as julle my nie kan hoor nie, dan hoed julle net of steek hand op of whatever.
Okay, ek sal dit vir jou sê. So, want ons kan jou ook mooi hoor nou, dis fyn.
Okay, wonderlik.
So if you don't can't hear him, just tell him, okay? Okay, so dan ek gaan hom los dat hulle aangaan, okay?
Ja.
Dankie.
Ek wil vir hulle werk gee om te doen.
Okay.
Ek sal dit aanstuur seker op Liesel se
Yes.
so voor
dis dood.
sou ons nie daarby uitkom nie.
Okay, dis reg.
Right.
Dankie.
Okay. Benice, I just need to clarify or see that if you can hear me, just say hi. Your mic is just muted, so you just need to unmute yourself.
Hi, Shaal, can you hear me now?
Yes, I'm hearing you very loud and clear, like I say.
This is Sherilyn. Benice is going to be here in a minute. She just
Okay.
quickly
Hi,
had to run
Sherilyn.
an errand. But you may start so long. I don't know who else is joining the class today.
There is someone else joining the class. Is this time suitable? 10:30?
Yes.
Okay.
Yes, it is. It is. You know, it's just sometimes your day does not work out as planned.
Okay, not a problem. Okay, good.
Okay, but she's here.
Okay, wonderful. I'll wait for her. It's not a problem.
Hello, sorry.
Hi, good morning. Welcome to the class. Before we start, I just want to get a roundup of what you've basically done this week. Okay, let's start with Kutso. Last week, we did some work energy theorem work stuff. Have you done anything? Have any one of you two done any work on that this week?
This week. No, I was going through the melting points and boiling points.
So you haven't basically on your time scale or schedule, you haven't started with work and energy?
No.
Okay. You are busy with organic chemistry and you are still working with physical properties?
Yes.
Okay. Right. You need to finish that. It's not a big deal in the exam. So you need to get that. I'm going to help you today. We're going to finish off that today. But that you need to finish because I'm not 100% sure what you are writing on in June. Oh, you'll be writing on everything you've done this whole year, but I'm not sure what other chapters are included in the exam. So the work and energy is a huge chapter. It's a lot of work. And basically you need to start working with that too. Okay, and Benice, what have you completed?
I've done work energy and organic chemistry. I'm done with that.
And now you're busy with Doppler, but just a question, is
Yes,
Doppler going to be
I'm starting with
examined? Are you going to be examined on Doppler in June? Is that part of your?
Yes, I am.
Okay, what else? What other chapters? Do you know? Or not know? If you don't know.
For physics is only Doppler effect for the test, and for the exam it's the whole of what we've done in the year.
Okay, so in the exam, it's work energy, Doppler, vertical projectile movement, momentum and impulse. Also, all the physics of grade 11. That is electrostatics, Newton, circuits, electrical circuits. So that's also great. You should be examined on all your grade 11 work as well. It's big. I know June in grade 12 is like a huge exam. Okay, so Kutso, you need to basically get going, up the tempo a little. What you need to realize, the physical properties is good to understand, but it's not a lot of marks in the exam.
All right.
Okay, all right, cool. So what we're going to do, I'm just going to run through all the questions you've got. So I'm going to do Benice's first because hers was submitted first. And then we're going to look at your stuff. And then I'm not happy with work and energy yet. I don't know if you can do it. And then I'm going to test you on that. If we don't have time, I'm going to send you some examples to do at home.
Okay.
Right. I need to find everything that you've sent me because it's like juice. Okay, Doppler effect. I'm not going to explain the Doppler effect. We haven't done that yet. So I'm only going to help you with that one example. Is that all right, Benice? We will
Yes,
do this as a chapter, maybe in a week or 3. Okay.
Okay.
So this is about, I don't think it will be more than 8 marks in the exam, the whole chapter. But it's something that you want. You want these marks because it's not that difficult. Okay, let's go through the example you have. Okay, Kutso.
Yeah.
You're not
Yes.
going to know what this is all about because you haven't studied it. Okay, during a study of a remote star, it's observed that the absorption line for red light is shifted from, let's say, 653 nanometer, a shift to 688 nanometer. Now, I guarantee you now, the reason you can't do the sum is because you don't understand what's happening here. Basically, you don't understand.
Yes.
All right, I'm going to explain this to you. I didn't understand the question too because it's the way it's formulated is a bit difficult. But let me explain this to you. Let's go here. If we take, this is an absorption spectrum. Basically what they do, you take the light of the sun and you shine it through a apparatus that will give you absorption lines. Now these black lines, I'm only referring to the top now. These black lines are elements like helium, potassium, beryllium, carbon, all of them where a specific element absorbs a ray of light at a specific frequency or wavelength, then it makes a black line. So what they're saying is basically, it's not a shift in the actual galaxy. They're comparing a shift of the sun, which was 553 nanometers. So they took a specific element. Let's use that one there. I don't know what it is, but let's assume that that was 653 nanometers. That absorption line there, I'm just going to highlight it with blue. Can everyone see that absorption line? It's about 653 nanometers. So they take that spectrum from the light of the sun, and then they take the light from a distant galaxy, and they take that spectrum and they compare it. Now, the light from the distant galaxy is the bottom one. That's the bottom spectrum. Now, that can either shift towards the left. So I'm going to compare these two. I'm going to make this one dark and this one dark here. I'm comparing those two lines. So both of them at the moment is 653. But now the light from the distant galaxy can move to the left. It's called blue shift. In other words, it becomes less than 650. Or it can move to the right, which is called red shift. It moves towards the red end of the spectrum, or it moves towards the blue end of the spectrum. If it moves towards the blue end of the spectrum, in other words, become a lower value, then the galaxy is moving towards Earth. If it moves towards the red spectrum, so that's 688 nanometers, so it moved to the red spectrum, that means the galaxy is moving away from us. Now, most galaxies are actually moving away from Earth. And you can use that difference in wavelength to determine the speed or the velocity at which the galaxy is moving away from Earth. Okay. So basically, we can just see by the fact that it's The initial wavelength was 653 and now it's 688. That is actually moved away. It moved toward the red end of the spectrum, so it's moving away from Earth. Okay, let's do that that question. Okay, during a study, a remote star, basically what they're saying, we compared the absorption spectrum of that distant galaxy with the absorption spectrum of the sun. So this is the one reading we got, and this is the reading of the galaxy. Okay, right. This is, and then they say it shifted from 653, it shifted to 688. Calculate the frequency of the source of the light, of the red light. Okay, that's basically what they're saying. Initially, that was the source. So I'm going to use this value here. So that's, I'm slightly confused by the question because the source is the same. If it's a galaxy, whether it's moving away, it's basically the same. So the source of the red light, you can also think about it this way. If this is Earth, and this is a distant galaxy, if it's moving away, then the light that will be emitted will make this ellipse. You've seen this in the chapter. Sound also does that.
Yes.
So if you sit here on Earth and you're looking at the galaxy with your eye, the wavelength will be higher than the initial wavelength it gives off. So the higher wavelength, 688 compared to 653, will give you indication that it's moving away. So let's say this is the source. Okay, and they tell you that's the source basically. So that makes it easier. Okay, let's do the calculation. Calculate the frequency of the source of red light. Okay, now C equals F lambda. That you did in grade 10. Okay, but that's back. So frequency is C divided by lambda. C is 3 times 10 to the power of 8. C is the speed of light in a vacuum, and that's a constant. And lambda is 653 times 10 to the power of minus 9. You can type that in a calculator. I think you gave the memo to me, you showed them. I just wanted to know which one they thought of as the source. What's that? That's like 4,59 times 10 to the power of 14 hertz. Do you have the memo there? Because I don't have it in front of me anymore.
Yes, I do.
Yeah, it's good. I see it on your WhatsApp. It's fine. Okay, this is the correct answer. Good. This is number 1, question 1. And then they just want you to also calculate the frequency of the observed light. In other words, what is the frequency of the light that you're seeing as you're looking from Earth? If you look at that, the light that galaxy emits, remember that those galaxies also will have a couple of suns. If you look at the light that galaxy emits, what is the frequency? You say C is F lambda. Did you get this part of the sum right?
Yes.
Okay, good. So we're going to go quick here. 10 to the power of 8. And now I've got 688 times 10 to the power of minus 9. And the answer was what? 4,36 times 10 to the power of 14 hertz. Okay, those are the two frequencies. So I have a higher frequency at the beginning and a lower frequency at the end. The higher frequency will have a lower wavelength and the lower frequency will have a higher wavelength because they're inversely proportional. Is a star moving away or towards the Earth? The stationary observer is the person on Earth. So is it moving away or is it moving towards? It's moving away. And you can give either you can refer to the wavelengths. So it's moving to a higher wavelength, or there's a red shift, which means that the wavelength is increasing, therefore it's moving away. Or you can say that the frequency is decreasing, and therefore it's moving away. You can either have one of those. Further away, the observer frequency is less than original. Okay, in their memo, they use frequency to explain. You can also use wavelength. The better answer is to say that the wavelength is increasing. There's a red shift or a shift towards the red end of the spectrum, and therefore it's moving away. It's called a red shift. And calculate the velocity. Is this the one you were struggling with? Velocity.
Yes.
Okay, number, this is difficult. I don't know or it's 3 or 4. I can't see. This is probably number 4. What is the velocity at which the star is moving away? Or the galaxy? Okay, right. You're going to use Doppler's equation. And that is the frequency L. What is L? Is V plus minus Vs. No, it's VL over V plus minus Vs. I'll explain this equation just now. And that's the frequency at the source. Now, the frequency L is frequency at the listener. This is the observer. So on this side, we have the frequency at the observer. And this frequency is the frequency of the source. Okay, and V, in this case, is going to be a constant because we're not working with sound. We're working with speed of light, so you can just put C values in there. You could have kept it as V. It doesn't matter. So in other words, you could have just kept it as V, but then V must be 3 times 10 to the power of 8 because that's the velocity of light. Right. So now, what is the L? That's the listener. So what frequency does L here? The one that we see from the distant galaxy is this one. 4,36 times 10 to the power of 14. So the listener, because Doppler effect is mostly used with sound, so it's called L for listener, but that's just the person observing. So we're observing a frequency of 4,36 times 10 to the power of 14. Okay, and then I have 3 times 10 to the power of 8. Now, what is the velocity at which the observer is moving while he's sitting in his chair? So it's just plus 0, or you can just leave it out. You don't even have to add anything there. So you can just ignore. If the observer isn't moving, because we are not moving, we're just observing, then that velocity of the L is 0. And then it's 3 times 10 to the power of 8. Now, this is plus Vs. That's the velocity of the source, which we don't know. And then the frequency of the source, they've given you that. That was the 653 nanometer wavelength, and we converted that into a frequency of 4,59 times 10 to the power of 14. So I'm just going to divide this purple value underneath the blue value. If I divide the blue with the purple, I get 0,94989, or you can have the silver calculator, type the whole equation in and say solve, and then it just solves Vs for you. And then I have 3 times 10 to the power of 8 over 3 times 10 to the power of 8 plus Vs. I'm just using plus Vs there because I don't know if it's a negative or a positive. The sum will give me that value. And then you solve the equation. You're going to multiply with this bracket right through. Okay, would you be able to do that?
Yes.
Okay, so you multiply this with that and Vs with that. And then you get Vs equals 1.58 times 10 to the power of 7 meters per second. And this is away from the observer. It's away from it. It's moving away. It's quite fast, eh? Do you know how fast that is? That's like almost, that's 10 times, more than 10 times less than the speed of light. But this is what? 4 times faster than the speed of sound. That is huge. It will give you an idea of how big the galaxy, how big the universe is. It's what? Yeah, let's not go there. Okay, is that better? Do you understand that slightly better?
Yes, I understand now. Thank you.
Refer to the Doppler effect and explain how a bat can determine the magnitude of and direction of an insect's velocity at night. Would you be able to explain that?
Yes, that one is fine.
Okay, good. Right, let's go. And you also wanted to talk about boiling points, is that correct?
Yes.
Yeah.
Both of you want to.
Yeah.
Okay. Right. I'm going to just run through those pages, good sir, and we're going to give special attention to boiling points. Now, the first thing you must realize, all these questions about viscosity, boiling point, vapor pressure, all those questions can be answered in the following way. How much energy is needed? How much energy is needed to overcome bonds? So the stronger the bond between molecules, the more energy is needed. Is that logic? Yes. So the stronger the bond, the more energy is needed. The weaker the bond, the less energy is needed. So a strong bond, that's an intermolecular bond, intermolecular force. So let's use bond or force. So the higher the intermolecular force, or the stronger the bonds between the molecules, the more energy is required. So high energy will give you a high boiling point. It will give you high viscosity. And it will give you low vapor pressure. A lot of energy will give you a higher boiling point or melting point. It will give you high viscosity, but it will give you low vapor pressure. What is vapor pressure? Basically, it's the pressure because of evaporation. So if there's huge amount of energy needed to overcome bonds, there will be only a little bit of vapor, and that will give you a low vapor pressure. Okay, so which one of these questions are we doing? Good, so because there's 10 pages. I can't do all the questions. I just need to do the important ones. So tell me on this page, which of these questions do you want to do?
Starting from question 2.
Okay, right. This one here at the bottom.
Yeah.
Okay, look at this molecule here. Everyone, give me a quick name. 1-chlorobutane. Is that right? Okay.
Yeah.
1-chlorobutane. It's got a boiling point of 78 degrees Celsius. On the left, on the right, I have what? 1, 2, 3. So that is 2-chloro. Let me just get a pen a bit thinner. That is 2-chloro. What? 2-methyl propane. Explain to me why the two compounds have different boiling points. Why is the boiling point of the one of the 1-chlorobutane higher than the 2-methyl propane? Both have the same molecular mass. Both of them have the same intermolecular force. So we can't use molecular mass. We can't use different types of intermolecular forces. Both is polar bonds. So this is both dipole-dipole. The one on the left will have dipole-dipole intermolecular forces. The one on the right will also have dipole-dipole intermolecular forces. They'll have the same molecular mass, same amount of carbon, same amount of chlorine, same amount of hydrogens. So it's not molecular mass. It's not different intermolecular forces. What is making the one on the right having a lower boiling point? It's a spheric form. The one on the left, there's the two linear molecules. And the surface area in which bonding can take place is bigger. The molecule on the right is more spheric. So the surface area in which bonding can take place is smaller. So it will have weaker intermolecular attraction. The force, the force at which the two molecules bond with one another will be actually smaller. The surface area rather will be smaller than the one on top. Do you understand that? Good so.
Yes.
Okay, so what is the reason? The reason is the more spheric 2-chloro-2-methylpropane will have a smaller surface area in which bonding can take place, and therefore it will have less energy will be required to overcome the bonds, and therefore it will have a lower boiling point.
Okay.
Remember, if the intermolecular forces are the same, it will be 4 marks. There's 4 things you need to mention. You have to mention the intermolecular force. You're going to say it's the same. It's both dipole-dipole. You have to mention also what? That the molecular mass is the same. Then you'll have to say that the surface area is different. There's another mark, and the third mark is about energy. Right, this one. What's this? There's no question on
This
this.
is the explanation.
Pardon?
This I
Oh,
want
this exercise 7.
yeah.
Okay. Look at the 2 molecules. Okay, you have to work a little bit on your photography just to get it sharper. Look at those
Right.
2. The relative molecular mass of both are the same. But there's a huge difference in boiling point. One is 64 degrees Celsius, and the other one is 80. Let's look at those 2. What are they? Let's write a structural formula for A. It's CH3, then CH2, CH2, so CH2, CH2. And then we have CO208. It's a C, then it's 2 oxygens, and then an H. So what's that? That's a carboxylic acid. So I'm going to draw one more. If you're working with intermolecular forces and you want to visualize it, you have to draw 2 molecules. So this is A. There's A. And B, we have CH3. And then another carbon with 2 hydrogens. And then another carbon with 1 oxygen. And then another carbon with CH3. So what do we have here? What's this? So on top at A, we have a carboxylic acid. At B, we have, it's a ketone, isn't it? Is that correct?
Yeah.
It's a ketone. This is 2 polar molecules. So this is dipole, dipole, dipole. And on top, what do we have? What type of intermolecular bonding do we have on top? Hydrogen bonding. Okay, can you now immediately see why A is such a high boiling point compared to B? Well, B has dipole-dipole. So the intermolecular forces at B. So you can say, even though the relative molecular mass is the same, the intermolecular forces at A is hydrogen bonding, and the intermolecular forces at B, which is an aldehyde, is dipole-dipole forces. The hydrogen bonding is stronger intermolecular force than the dipole-dipole bonding, therefore more energy is required to overcome the bonds at A, and therefore it's got a higher boiling point. You see, if you don't draw these diagrams, you might struggle. The hydrogen bonding is between this hydrogen here and this oxygen there. There's 2 sets of hydrogen bonding in a that one there and that one there. Okay, cool. Happy?
Yeah.
Next question. Which one are we doing here?
This is what is it? You can go to the previous question, and you'll see the table of A, D. I don't know if they're in order.
I don't have that. Oh, there we go.
Yeah.
Okay, what do we want to know? We're going to compare, let's compare A, B, C, D, and E. Can anyone explain to me why D has a higher boiling point than A? It's 125,8 compared to 36. We have what type of intermolecular forces at both of them? What is the intermolecular forces at A? It's called London forces. Are you with us, Bernice?
Yes.
Two A molecules will have London forces. D will also have just London forces, but D has a longer chain than A. So there's more surface area in which London forces can bind, or where there's more London forces, there's a longer chain. So there's a bigger surface area in which bonding can take place. So we'll need more energy at D. Compare D with E. The molecular mass is the same. We have the same amount of carbons and hydrogens, but D has a higher boiling point than C. Okay, Kutsa, why? Why does D have a higher boiling point than C?
Because it's less spheric.
E is more spheric, or D is less spheric, yes. And therefore the surface area at E is less than the surface area at D. Therefore you need more energy at D, or you need less energy at E. Can you see that?
Yeah.
Good. This is going to be exactly the same. They want you to probably put this into higher or lower boiling points. Let's compare this molecule, just these two, that one and that one. Which one of those? Let's make this one A and this one B. Which one will have the higher boiling point? A or B?
A.
Why?
Because it's hydrogen bonding.
Yes. And B, what type of bonding does B have? Dipole, dipole.
Dipole, yeah.
Because we have, if you doubt, you can just write it. I've got 4 carbons and then a bromine and another 4 carbons and another bromine. So that's polar, polar, dipole, dipole. Look, there are London forces as well, but the main intermolecular force here, the one that counts, is the dipole, dipole, compared to the alcohol on the hydrogen bonding. Hydrogen bonding is stronger. Okay, Bernice, you need to ask questions with regards to boiling point if there's certain things that you still don't understand.
Okay.
So melting point and boiling point will have the same reasoning behind it. Same reasoning. It's a different phase, just a different phase that is changing. Can everyone hear me quite well?
Yes. Yeah.
Yes.
Okay. Which compound? Okay, let's choose a question. 6 or 7.
You're breaking up.
Pardon?
Okay, I can hear you now. Never mind.
We can do 6.
6. Which compound in the next pair has the highest boiling point? I want you to look at it and make a decision. If you can't, then you must draw it. Then the one on the left is a carbon, and there's 3 other CH3s. There's only one way we can draw that. There's the 3 CH3s, there's another carbon, and there's another 3 CH3s. That's the one on the left. And then the one on the right, we have CH3. We have CH2, CH2, so there's 3 of them. And then we have CH. And then CH3. And then a CH2. And then a CH3. Which one of those, A or B, will have the highest boiling point or melting point? B. Why? You need to name the intermolecular forces. Both is London forces. Both are London forces. A is a much more spheric molecule than B. B also has a higher molecular mass. Therefore, B will have a bigger surface area in which bonding can take place. So more energy will be required to break the bonds or overcome the bonds at B. So B has the higher melting. So B. Okay, isomers of C7 or C14. Okay, which isomer will have the lowest boiling point? Or melting point? What is melting point? Okay, let's just establish that this is the lowest value, top one, and why. If you don't know, you have to draw that structure. It will be more spheric. Just, I mean, A and B, you can't really compare A and B with one another. There's like a 1 degree difference. But you can compare A and C with one another. A is spheric and C is not. C is linear. I don't know. Study the tendency in melting points for the following isomers and then do what?
Ask to draw the structural
Formula.
isomer.
They are all
Yeah.
structural isomers.
You have to draw them on the next page. I think.
Yeah,
You want to do that?
8.1.
We're not going to do all of them. Choose one that you want to draw, and then we work from there. Unless you want to draw all of them, because you don't know how to draw them.
Stroke
I'm
B.
struggling to hear you, Kutsa.
Can you hear me now?
Yes. Which one do you want to draw?
B.
B.
Yeah.
CH3. CH2. CH2. Another CH2. Then just CH. And then CH3, two of them. So the only way you can draw another CH3 is by having that. That's B. And that explains why it has such a low melting point. It's kind of very spheric. If you compare it with it, if you just take this one, and you copy it, and you paste the next one underneath it. It doesn't want to be copied now. So if I paste another one underneath it, look how far away these two molecules are from one another. It's quite spheric as well. And that will give you a very low area where bonding can take place. Well, if you compare that with C, C doesn't have any side branches. It's just flat. So linear, basically. Okay. I'm not giving too much attention to something that counts 2 or 3 marks in the exam, 4 marks maybe. Okay, which one do you want to do here?
Definitely 9.1.
Write down the homologous series in which compounds A to C belong. Okay, I can just see what it is. Is it CH3, CH2, CH3? Okay, what's the homologous series here? All of them has got the same. No? Each one's different. I can't see there. It's a bit difficult to see. So this is single bonds. So what are these?
Wait.
Okay.
And
Okay, and the next one, is that a double bond there?
Yeah, it's a double
Yes.
bond.
CH double bond CH2, something like that.
Yes.
Okay, what is
yeah.
this?
It's an alkene.
Yes. And the last one is a triple bond. So alkene, alkyne.
Fine.
Yeah. Okay. Place the compounds in sequence according to decreasing strength in intermolecular forces. Okay, you can't really do this, to be honest, because double and triple and single bonds are just difficult. There's no rule. But what you can do, you can look at their boiling points. And you can see that the alkyne has got the lowest boiling point, so it will have the weakest intermolecular force. Is that correct?
Yes.
And
Yes.
the double bond is got, I can't see there. Is it minus 48? Oh,
48, yes.
sorry, I'm wrong. I can't really see that. So this is minus 23 is the highest boiling point. This is lowest, highest, and middle. It's very, very difficult on my screen to see. So negative 23 is the highest boiling point. So that will be the highest intermolecular force. So we must, according to decreasing strength. So I'm going to do C is bigger than
Fine.
A is bigger than B.
Yeah.
There's not a general rule that alkynes are always higher. It's just, it depends on where the triple bond is. Okay. Name the intermolecular forces that exist between the molecules. They are all London forces. Explain the difference between boiling points between B and C. I can't. According to me, saturated and unsaturated bonds doesn't really play a role in boiling points. It depends on where the saturation in the bond is. I would love to see the memo on B and on this one, 9.4.
They say that due to triple bonds, the molecules of alkynes are more likely to be polarized than molecules of alkenes. Alkenes have stronger London forces.
Alkenes.
Yes, that's what they're saying.
So why does it have a lower boiling point then, if it has stronger London forces?
I don't know.
That's a problem, isn't it? Explain the
Yeah,
difference. Just read that answer again, please, Beneath.
due to triple bonds,
Yeah.
the molecules of alkynes are more likely to be polarized than molecules of alkenes. Alkenes have stronger London forces. It's likely to
Stronger
be
London forces should have a higher boiling point. Okay, anyway, question. There is no hard and fast rule. Because these are small molecules, they're both carbon, 3 carbons, you can compare them. Because that's not really anywhere. You know, the double and the triple bond can't be in anything else but on carbon 1. So these can be compared. I also have it then, if we've got the same, around about the same molecular mass, then the triple bond will be a higher intermolecular force, but more polarized. I would say it'd be less polarized. Anyway. Okay, anything else here?
I think I have a general idea now.
Your book has got a lot of questions on this. If you get the hang of it and know how to answer it, then you should be fine.
Right.
Okay. This page, good sir?
This page. This is basically the same stuff. So this is basically the same stuff going
Yeah.
forward.
Okay, the way you can actually get all these to see if they're liquid or a solid or gas at probably at room temperature, that's what they're probably referring to at room temperature, is just to look at their boiling points. Classify the following organic solids, liquid or gases. When? At what temperature? They should have said room temperature. Okay, 25 degrees Celsius, yes. You can look at their boiling points and their melting points. Then you'll find if they're liquid or a gas or a solid at room temperature. They'll have a table. You can't know it off by heart. Right, let's go back. And look at work and energy. So we are there at the work and energy theorem still. I want you to help me with this example because of what you know. Stationary wheelchair. Stationary means its velocity is 0. Of a mass of 16 kilograms is not secured at the top of the slope with a vertical height of h. The wheelchair rolls down 12 meters on the slope and reaches the bottom so the velocity at the bottom of the slope is 1.5 meters. The total frictional force acting on a wheelchair is 31.17 Newton. Calculate the work done by the frictional force as the wheelchair rolls down 12 meters. 5.1 on your own. Someone's got 2 speakers on for me, so I'm repeating myself. Just put your speakers behind your mic or in front of your mic if you've got loose speakers. Quickly do that. Work is force delta x cos theta. So if you want the frictional force, it's the work done by friction and F friction or just friction. This is really easy. This is everyone has this sum right. 100% for number 1. If you have an answer, you can give it to me. Okay, it should be finished. The work done by friction is the frictional force. That's 31.17 times the distance, which is 12 meters, cos 180. Because the angle between the movement and the frictional force is 180 degrees, and that is 374.04. Negative.
Yes.
7.
Negative. Yes.
Okay, now just a question. Jules, do you actually leave the answer as negative? What do you actually do in your, what does your textbook do? Leave it negative or give a direction?
No, you give a direction.
So they want you to just give direction and not leave it as negative. The work done by
Yes.
friction is 374.04 joules upslope movement.
Yes.
Okay. Good. 5.2. I want to know what is the height. What's that important question you need to ask? The important question is, what formula are we going to use? Are we going to use V net or W net, F net, delta X cos theta? Or are we going to use W net is the change in kinetic energy? Skip the top one because we're not going to work out F net. Or we're going to use VNC is the change in kinetic energy plus the change in potential energy. Which one do you think is going to be the easiest? Both of them will work fine. Which one are we going to use? Which one do you think is the easiest one?
The last one.
Yes, the last one is easier. Why? Let's just quickly draw a free body diagram. We have the normal force, we have friction, we have FG perpendicular, we have FG parallel. If I use the last formula, I only have to be concerned about these two forces because they are the only two non-conservative forces. If I use V net, I have to use this. This is a problem. I don't want to calculate that unnecessary, but both will work. So I'm going to use VNC is the change in kinetic energy plus the change in potential energy. So this is the work done by friction plus the work done by the normal force. Those are my two non-conservative forces. And change in kinetic energy is half times the mass times the final velocity square minus initial square plus mg final height minus initial height. And that's what we want. I'll show you just now how we could have used the V net as well. Okay, let's go. We have calculated that, but now very important, you have to write this negative value too, because that value you're going to use in the sum. So if I want to carry that value over, it's negative 374,04 plus 0, because the work done by the normal force is always 0, while the normal force is perpendicular to the movement. So it's cos 90 degrees. Half. How much does this weigh? 16. The mass is 16. The final velocity was 1,5 squared minus 0 plus the mass, and g is 9,8. The final height is 0, and the starting height we don't know. That you can just calculate. Let's just do that. Everyone. Okay. Minus 8. See if you can get a height. My height is 2.5 meters. Calculate that. Kucho, is it your speaker that's repeating sometime? What do you have? A speaker?
I don't know, because then the computer, I'm using the computer alone. There's no speakers.
Oh, okay. Fair enough.
Yeah, I also don't have speakers.
Maybe it's me. Maybe it's my mic that is. Samsung meter. No, I'm fine. Just going to take the volume slightly down. Can you still actually hear me quite well?
Yeah.
Yes.
Even if I take it down more, can you still hear me?
Yes.
Yeah.
Yes.
All right. Automatically adjust microphone volume. That is the problem. Okay. I'm testing the mic. Better?
Yeah. 2.5, yeah.
Right. 2.5 meters?
2.5 meters? Yes.
Yes. Yes.
Okay. Let's just do it on the other method as well. Right. Help me out. V net is the change in kinetic energy. Now, V net consists of these two forces. So I have the work done by friction plus the work done by the parallel force. And that is half m V final square minus V initial square. What I'm going to do, I'm just going to mute. I'm just going to mute both of you for a while. And then if you want to say something, just unmute yourself. Okay. I think that's just going to help with that feedback. Good. Right. Now, this is a small problem because it makes the calculation difficult. Okay. The work done by friction, we've done, that's negative 374,04 plus the work done by the parallel force is the parallel force, Fg parallel, times the distance, delta x, times the angle. And that's half times mass, which is 16. The final velocity is 1,5 square minus 0. So that I don't really want to work out. So what I'm going to do, I'm going to take the negative 374 over to the side. So it becomes positive 3. Just to get rid of it on the left-hand side. And then I can just type in that half times 16 times 1,5 square. So that's 8 times 1.5 square. That's 18. So now this end, I have FG parallel, which is mg sin problem, alpha. I don't have that angle. You see, delta x, which is 12, cos 0 degrees, because the parallel force is in the same direction as the movement. Okay, so now I have, what's that, 392,04. Is that correct? Yeah. Now I have a problem here. I have the mass, it's 16. I have 9,8. Then sin alpha is what? Is opposite over hypotenuse. So sin alpha is h over 12. And that times 12. So those two cancel. And then I have 16 times 9,8 times height equals 392,04. Divided by 16 times 9.8. I get 2,5. So unmute yourself. Talk with me. So basically what makes this harder is that you actually get to a point here in the sum where you realize you don't have this angle, and then you can panic. That's why the other equation was actually slightly easier to work with. So what I'm going to do, I am going to send 2 examples. This is not the example we wanted. I'm going to send 2 examples to you. No, where's examples? Here we go. We've done that one. There's the other example. So I'm going to paste that. I want you to do that for homework. You just get this. Paste. Huh? Copy. It doesn't want to paste. Some reason it doesn't want to paste there. Let me just do it another way. Find another way. Can you actually see the size now? Was it too big?
No, I think it's fine.
Okay, let me just paste this quickly into as a WhatsApp. There's one example I want you to do for homework. I know you've got lots of others, but it's kind of funny that you're not struggling with anything in this chapter. It might be that you are getting 98% for science, and then you won't be struggling with a lot of them. There's two examples I want you to do homework. One of them is mixing up work and energy with momentum and impulse. It's just like a combination sum. You have to do both in one sum. Okay, and then I'll see you next week again for science lessons. I want you to finish off all the organic chemistry. You have to finish that chapter, and you must be either busy with work and energy or Doppler. And then next week we'll be doing Doppler effect with various examples,
Right.
and we'll still be playing around with work until you start new chemistry, because there's a couple of chapters of chemistry, I think. Yeah. Do you just, if you have the schedule in front of you, you might just start if you have to do acids and bases. When are you
So
doing?
you're picking up now.
It's fine. You don't have to have it in front of you. If you don't have it, we don't have it. Then we can just go. But acids and bases is a very important chapter, and you need to set out some time. Start doing it this term. You need to set out some time for that, because that can be problematic.
Yes, I have to do that.
Acids and bases
Yes,
and pH calculations.
yes.
Okay, that is a problem. That's a difficult chapter. Right. So the Doppler is important because it's 8 or 9 marks for free if you get it right. But the acid and bases would be much more. It would be 15 to 20 marks.
Okay.
Don't rush. Just work out the stuff in the term But Kutso, you might just want to speed up a little bit. Okay.
Okay.
Keep well. I'll see you again next week.
Thank you.
Bye.
Thank you.